the reaction which I'm going to do now is decomposition reaction. So just remember here, as the name suggests, here a single reactant, just remember, a single reactant decomposes to two or more products, okay, by absorption of energy. So the energy can be either in the form of heat, electrical energy, or or uh, or some energy of sun, that is photolytic energy. Okay, so basically decomposition reactions are classified into three types, okay, based on what energy they absorb. Okay, if they absorb uh, thermal energy, okay, that is the heat energy, then we call it thermal decomposition reaction. Thermal decomposition reaction. And if it absorbs electrical energy, we call it electrolytic decomposition reaction. And if it absorbs energy of the sun, that is solar energy, okay, we call it photo photolytic decomposition reaction. And remember, okay, decomposition reaction is reverse of combination reaction. And in combination reaction, we have learned that most of the combination reaction were exothermic in nature. That means in those situations, the heat energy was released. Okay, the energy was released. Here in decomposition reaction are endothermic in nature. Here, most of the time, energy is absorbed. That's why it is endothermic in nature. Okay, so here thermal energy is absorbed, here electrical energy is absorbed, here energy of the photon, okay, is absorbed. That's why it is photolytic decomposition reaction, this is electrolytic decomposition reaction, this is thermal decomposition reaction. Now we will do each one of them in detail. So let's learn about thermal decomposition reaction first. Okay, so as the name suggests, okay, it's a type of decomposition reaction, okay, in which thermal energy is absorbed. Okay, so I will give you, or heat energy is absorbed in simple. Okay, it's a type of decomposition reaction in which heat energy is absorbed. So I will give you a, okay, very favorite of examiner. Okay, when iron, okay, sulfate crystal is heated. Okay, iron sulfate crystal is heated. See, iron sulfate in crystalline form, it is green in color, light green in color, light green, okay, in color. Ferrous sulfate crystal, okay, it exists as water of crystallization. That water of crystallization we will learn later, okay, in acid base chapter. But also just remember what is water of crystallization. When a molecule has certain number of water, okay, molecule in it attached to it, okay, then that is known as water of crystallization. That is when certain substance is hydrated. When certain substance is hydrated to a fixed number of water molecule, okay, we call it water of crystallization. So here, okay, that ferrous sulfate is attached to fixed number of water molecule, that is 7 number of water molecule. That's why it's also a water of crystallization. And here in crystalline form, its color is light green. Okay, when we burn it, what will happen? Okay, when we burn it, we get ferric oxide, okay, sulfur dioxide, sulfur trioxide, okay, and water of crystallization. Obviously this is not balanced, so it is your duty to balance it. Okay, but I know that if we simply see this side, we have 7. If we multiply with 7, okay, now we are getting how many hydrogen here? So okay, we are getting 14 hydrogen here. Okay, this side also 14 hydrogen here. Okay, then oxygen we are getting how much? Okay, oxygen this side it is, okay. Oh, what if we multiply with 2? Yes, if we multiply with 2, now iron this side is 2, that side also is 2. First I started with the metal. Okay, it's better to do with metal fast. Okay, we are doing heat and trial method. So if I balanced iron, so here iron is 2, that side also 2. Okay, then count the numbers of let's say sulfur. That side it is 2, this side it is 2, that side it is only 1. So let's multiply. Oh no, that side also it is 2. 1 plus 1 is 2. Then oxygen at this side it is how much? 4 to the 8, 8 plus 7, 8 plus 7 is 15. That side it is how much? 3, 4, 5, 6, 7, 8. 8 plus how much will be 15? Okay, if we multiply this with 7, it will be 15. Okay, so now I think everything is balanced. So here we simply needed to multiply with 2 and that side with 7. Okay, balancing is not important for particular questions. Okay, why? Because I'm teaching you thermal decomposition reaction. Just remember that here ferrous sulfate crystal is heated to get, just remember that here the color of the ferrous sulfate crystal was light green. This side, okay, it has lost, okay, water. That means it has dehydrated, and then after further burning, what it has become? It has become ferric oxide, whose color is reddish brown. Just remember that its color is reddish brown. Okay, it is reddish brown in color. And one more thing, this sulfur dioxide smells like what? Okay, it smells like rotten egg. Okay, we often call it okay, smell of burning sulfur. Smell of burning sulfur. Burning sulfur. Okay, and also you can relate it to burning of rotten egg. Okay, so just remember that is the test for sulfur dioxide. Understand? No? So if you smell the burning of a certain kind of smell like rotten egg, then surely it is sulfur dioxide. Okay, and here just remember that initially this thing was light green color, later it became reddish brown due to formation of ferric oxide. So this is thermal decomposition reaction, okay, of ferrous sulfate crystal. There is one more okay, classical example of thermal decomposition reaction which you should know. Okay, when lead nitrate is heated, PbNO3 2 is heated. Okay, lead nitrate is heated. Okay, so this is also very favorite of examiners. Okay, so when lead nitrate is heated, just remember what are the things formed. Okay, so the stuff which are formed is, okay, lead, okay, oxide, then you get nitrogen dioxide. Okay, and what else? We get oxygen. Okay, just remember that. So these are the things which we get actually. Okay, when lead nitrate is heated, we get lead oxide, nitrogen dioxide, and oxygen. Okay, just remember that. Okay, initially this lead nitrate obviously was in it was a bulk. Okay, it was white color. Okay, white in color. Okay, after heating, okay, the lead oxide which we got, actually the color of lead oxide is yellow. Okay, so basically the transition happened from white color to yellow color. Okay, and when the gas was evolving, okay, the gas had reddish, okay, reddish brown color. Just remember that when the gas was evolving, it was reddish brown in color. Okay, and okay, that is because of the evolution of nitrogen dioxide. And oxygen, you know, also got evolved. But how do we know that? So if we simply, okay, if there is a test tube, okay, or anything, crucible, wherever we are heating it, so let's say here we have lead nitrate. Okay, so if we are heating lead nitrate from here, okay, so let's say lead oxide will remain here, that will be yellow in color, but nitrogen dioxide and oxygen will come out. So the color of the nitrogen dioxide is visible, it is reddish brown in color. Okay, but oxygen how do we test it? It's not visible. So if we just bring, let's say this is a burning, not burning, just a splint, okay, सुलगता हुआ लकड़ी, okay. If we are just bringing it near that gas, it will ignite, okay. Okay, this that वो सुलगता हुआ जो आग था, it will just ignite, okay. So that is it, okay. So if you just bring a burning splint near it, okay, it will ignite nicely, okay, due to oxygen. Just remember that, okay. So that's all from thermal decomposition reaction, okay. Thank you. We have some like calcium carbonate also, we heat, we get calcium oxide, carbon dioxide, okay. There are many examples, so you can do those also, okay. Thank you. That's all.